Appreciate you too, thank you. Thanks everyone. My name's Mancuso. I'm Principal Systems Engineer for Western Digital, the Data Center Systems Division. Today I'm going to be talking about Nvme over Fabric and some things that Western Digital is doing in that regard. It's a new storage technology which still it's bleeding edge at the moment, and there's a lot of work being done in this regard, but I think it's going to change the way we all look at infrastructure. To begin with, look, brief overview. I mean, people say, don't you guys just do hard drives? Well, no, we have a whole data center systems division now, an enterprise division. We have 3,000 odd customers. We're growing. We're growing at a rate of about 150 customers a month. And we shipped 3 exabytes last year. That's just the enterprise systems. But I'm not going to talk too much about that because this is not a shareholder meeting and I don't need to tell you how well we're doing. What we're about is silicon to systems. So we make the NAND flash. We make hard drive heads, we make a lot of components that go into hard drives, we make the hard drives themselves, we make SSDs using the flash. Some of the NAND we sell to other vendors as well for their technologies. Firmware, memory controllers, SSDs I mentioned, we integrate them into platforms, so we have hyper-converged storage systems. Platforms like JBODs and things for you to build your own infrastructure with, but also systems that do unified SAN or NAS, object storage, and all kinds of other things as well. And this allows us to innovate in a quicker manner because we control everything across the whole supply line. So if we want to add a new feature into the devices, it's quite easy for us to take advantage of them, those new features into the systems. We can also ensure quality and greater interoperability. So since we're talking about Nvme over Fabric today, and this is a quick slide to show you all our Nvme portfolio. This is not our entire portfolio of systems, but we build everything from Nvme drives, cards and SSDs, memory expansion devices, which is something memory intensive applications can really take advantage of. That's another topic for another day. Platforms, something new called composable infrastructure, which leverages Nvme over Fabric, and I'll be talking more about that. In fact, that's what the majority of this presentation is about. And Nvme all flash arrays. Now, just quickly before I embark on Nvme over Fabric, I wanted to slip in a little announcement, because recently there was in the US Flash Memory Summit. Flash Memory Summit happens every year. It's becoming a very big event where a lot of storage vendors introduce what they're working on and about to release to the market. So all kinds of new products come out all the time. We have just announced the 4-node Nvme server, and we have 2 certifications with it currently. And we're concentrating on these 2 vendors, Weka.io and Accelero, for ultra-fast file system on one side, and RDMA capable block storage on the other with respect to Accelero. So scale out file system or scale out block. And as you can see from the performance figures, quite significant numbers. Without further ado, let's talk about Nvme over Fabric briefly. So I think everyone is pretty clear on what Nvme is these days. If you're not, it's an open device interface specification for accessing non-volatile storage or storage memory or flash. You can insert any of those in there via the PCI Express bus. The Express in Nvme Express comes, in fact, from PCIe Express, so PCIe. The best way to look at Nvme is SCSI, okay? It's SCSI, instead of for hard drives, it's for storage memory. Similarly, everyone has heard of iSCSI, and you kind of know what that is. So iSCSI is really SCSI over IP, and that's the best way to look at Nvme over Fabric. Same thing. So think of Nvme over Fabric as you would iSCSI. Nvme it gives you a lot of advantages, lower latency, direct access to the memory of the SSDs, greater throughput, lower latency, and higher IOPS. And a lot of people tell me that they're not ready to take advantage of the performance that Nvme gives, but rather quickly you'll find that Nvme is going to replace SAS or SATA SSDs in the very short term. So you may not need that performance just yet, but you're going to get it anyway. So we've introduced a new value line of Nvme drives as well. So basically Nvme is going to be the interface of choice for talking to any class of storage memory going forward, whether you need the performance or not. So why Nvme? I mean, I've already touched on that a little bit. It was designed for flash memory to take advantage of the parallelism of the chips, of the memory chips in the SSD, and it's key to accelerating data workloads. You have increased number of command queues. In fact, there are 64K command queues with the Nvme protocol. And as I might as well flick straight to that right now, each command queue has a queue depth of 64K. So that's quite a number of outstanding commands that you can send to the Nvme device, and the CPU can go off and do something else. So it's much higher bandwidth than SAS or SATA, which was designed for legacy hard drives, and improves TCO, because you sometimes can save money on software licensing because you'll need less cores, you'll find, when you have a more efficient storage subsystem. And NVMe fabrics and NVMe devices will be the building block of the data center, and I'll explain a bit about that. So, you know, why are we putting NVMe on a fabric? Well, fabric has a lot of advantages because everything connects to everything. So it's an any-to-any connection, and basically NVMe over fabric extends the capabilities of NVMe outside the server, in effect extending the PCIe bus out the server to another server or across the data center. Why would you do NVMe over fabric? Well, you have access to features like direct memory access. More appropriately, remote direct memory access, which I'll talk about in a second. And NVMe over fabrics, as I've already mentioned, extends the benefits of NVMe, the low latency, to external storage. What we have seen is a revolution going towards hyper-converged, right, or converged rather, where the NVMe devices are installed directly into your compute nodes. Why we're doing that is because a SAN is a traditional bottleneck, I guess. We sort of reached the limits of what you can do with a SAN in certain respects. So given that you can put NVMe in a SAN and accelerate it a little bit, you're still not getting the true performance. So getting the really low latency, you have to put the NVMe devices into the compute nodes. But by using NVMe over fabric, you can go back to having your centralized storage server and all the benefit that brings, as well as taking advantage of the lower latency. So in effect, the low latency given by NVMe over fabric enables you to look at remote storage as if it were local. RDMA, I mean, we can touch on this briefly, but it's a way that a storage adapter on one server can access the memory directly on another server. So direct memory access, local direct memory access, obviously came about many moons ago to not have the CPU involved in every transaction, right? So if the CPU is taking some data from the storage adapter and it's feeding it to the application or whatever, it's often heavily involved in the transaction, passing the blocks and whatnot. With direct memory access, the CPU just says, right, there's actually a direct memory controller. The CPU says, right, you go ahead and use this chunk of memory. I'm going to go off and do something else. When it's done, let me know. So the storage adapter talks to the memory directly. So what we're doing with remote direct memory access is enabling that across servers, across a network. Let's, however, whilst RDMA is an advantage of NVMe over fabric, it's not a given all the time, because there are protocols that support RDMA and there are protocols that do not. So protocols that support RDMA are ROCE, which everyone calls ROCE, which stands for RDMA over Converged Ethernet. IWARP, which I crossed out the definition there because I've since seen a presentation where people heavily involved in IWARP have said that it was never an acronym Internet Wide Area RDMA protocol. It seems to have been retrospectively added. I'm not sure what is the truth, but irrespective, it's an alternative offering to ROCE. And then there's InfiniBand as well, NVMe over InfiniBand. Now, the other two protocols, however, NVMe over FC and NVMe over TCP. The NVMe over TCP has not been standardized yet. I understand there are some products out there that do NVMe over FC. And look, that's largely to take advantage of existing infrastructure where people might have an extensive investment already in FC. So just to reinforce, RDMA effectively bypasses the shared storage controller and enables you to access those drives as if they were local, or the volume or the RAID volume, whatever it may be. So both ROCE and IWARP, I'll concentrate on them first. They both run over Ethernet. You can look at ROCE as InfiniBand over Ethernet. This will become a little bit clearer because on a further slide. There are slight differences. ROCE needs RDMA capable network cards. and newer switches with data center bridging features, okay? And that's how it achieves data center bridging is a set of enhancements to the Ethernet protocol that provide transmission reliability, right, without the complexity of TCP. RoCE is said to have obviously, doing RDMA or doing RoCE, RDMA over converged Ethernet, gives much lower latency than doing NVMe over TCP, and 20 to 100% performance increase. There was a version 1 RoCE which was non-routable, and there is now a version 2 which is routable. I think that's how the acronym for IWARP came about, because I think early on they were differentiating it by saying IWARP was routable whereas RoCE wasn't. Maybe that's because of when RoCE version 1 was around, but now that's a moot point, right? So maybe that's why they're changing that acronym or something, I'm not sure. In any case, look, IWARP, rather than having the data center bridging features on Ethernet, it's basically using TCP. So RoCE is UDP, okay, with some lossless features provided via data center bridging. I've seen some reports suggesting that IWARP can achieve up to 67% greater performance over TCP using SMB Direct, and it seems that in some literature I've read, IWARP is the recommended protocol for Microsoft environments, but I've seen SMB Direct work quite happily over RoCE and InfiniBand. Which is better? I'll leave it to you to decide, and I think that's an argument amongst the network vendors, really. I wanted to share this slide here from SNIA, the Storage Networking Industry Association. We're members, and I'm allowed to present this slide as is. It comes from a very interesting presentation. They had a debate on this. It was a live webcast. And basically on the left-hand side, the RoCE vendors are listed there, and the guys behind IWARP are listed on the right, okay? And this also shows the protocol stack and the differences between InfiniBand on the left, okay? RoCE v1, where you can see that the Ethernet link layer was introduced, and then RoCE v2, where the UDP replaces the IB network layer. And then there's IWARP, and so you can see the differences there where there's the UDP instead of TCP in the case of IWARP. So I touched on these differences. Obviously IWARP just relies on standard TCP to provide the transmission control, and whereas RoCE relies on the DCB features. So you might have to invest a little bit more in your cards perhaps, or your adapter cards, and make sure your switches are modern. So people that are proponents of IWARP will say, well, you don't have to change anything. However, RoCE seems to be achieving better performance at the moment, so from what my understanding. So I'm going to, one of my last slides is a link to this SNIA presentation, and there's also YouTube and a Bright Talk video as well, and I recommend you go have a look at my resource slide, because we will share these slides. Have a look, there's a lot of interesting information there. Then, briefly, NVMe over FC and NVMe over TCP, both were designed to take advantage of legacy infrastructure. NVMe over fiber basically just encapsulates the NVMe packet into the FC datagrams, and off it goes. And NVMe over TCP, there's work being done on it, and I understand that it's not been standardized just yet. It's not the same thing as RoCE, and it's certainly not as fast. And neither does RDMA, I'll stress that. So where are we on the NVMe roadmap, I suppose? I mean, we're seeing that it's starting to become much more readily deployed. That's plain NVMe. If you're doing NVMe over Fabric, it's still a bit of an early adopter kind of scenario. But SAS or SATA, in the case of Flash anyway, is diminishing, okay? Already, laptops are not coming anymore with SATA SSDs or M2 NVMEs. It just makes no sense to have all these different interfaces when NVMe achieves or gives so much better performance. And the difference in cost of the interfaces come down to be basically negligible. So what does NVMe over Fabric let us do? It doesn't just allow us to talk to flash or storage. We think that our vision for the future involves a term we call composable infrastructure. So what we're suggesting is that using a fast fabric, you can, in theory, connect anything together. So you can connect servers to storage, but you can also connect compute to disk and flash to FPGAs and GPUs to CPUs and other things, okay? And I'll talk a bit more about this. What we're saying is this. That's a picture of one of our storage servers, and it contains all these components. It contains CPUs, GPUs, FPGAs, memory, maybe a bit of flash and some disk. But then you're working with what you've got in the box and the specifications of that box. What we're saying is that potentially you could take all these discrete components and combine them into a virtualized server of your choice. This is, in effect, you could also look at it as virtualization outside the chassis. Virtualization across your infrastructure, potentially. So you could potentially compose a system that looks however you like for whatever workload you choose. And picture it a different way. This is all these discrete components connected to a switch or a fabric. Okay, so in theory, this could allow you to take a slice from some CPUs somewhere, a GPU, flash in this case, and create virtual system 1, like that. Or you can then create another system with some FPGA, because it's got some specific task or something. You can add some memory, add some disk, add some flash, and you've got another system designed for that workload, and so forth. Okay, so that's our vision of open composable infrastructure. So that is all reliant upon an API, which we are working on, and we have made open and submitted it to various industry bodies for approval. And so far, we've got some vendors who are on board with this. Some of them are mentioned here. So Mellanox and Broadcom are both partners of ours, not only in the Nvme over Fabric space, but also working on this composable infrastructure with us. DriveScale and Caminario are providing an orchestration layer via our API. And so we want this API to be open, and we want the industry to come on board and support it and be interoperable with it, because some people, other vendors are working on composable infrastructure, but it has to be all their equipment. It has to be their switches, their compute nodes, their disk arrays and things like that. We think you should be able to add parts from anybody and make it work. I know it's an extreme vision, because I think it's something that the industry has always talked about. But no, I think there's some serious drive behind this. We've got other partners as well that are involved. And a couple that are noteworthy, IDITICOM and Xilinx, who are providing storage co-processors and things, which I'll go into in a little while. So one of the things that we have announced now, this is a valid product, because we think there is some use for something like this. This is a Nvme over Fabric. It supports RoCE. It's a 3RU storage device, or it's actually made up of 10 storage devices that you insert into it. Each of these devices on the far left is a flash module. So it's full of flash. And it, on the back of it, has two 50 gig Ethernet connections. And those Ethernet connections are shown outside the box there on the right. And basically that's 1,000 gigabits of connectivity to this high-speed flash, giving you potentially 120 gigabytes a second of throughput on this device. And if I remember correctly, it's 20 million IOPS. Okay, it's a lot of performance, perhaps performance that a lot of people don't need or can't take advantage of yet. But obviously, and it's also up to 600 terabytes in 3RU, which we think is pretty efficient. So, as I said, it supports RoCE at this point, so we're partnering with Mellanox on this product. It's capable of serious performance. Behind it all is, again, what we call the open composability vision, and an API that allows you to log into it via REST and monitor and administer the device. Now, we've also got other visions, and this sort of thing was announced. We had a prototype at Flash Memory Summit, which is, whilst the OpenFlex F3100 is a valid product and available for ordering right now, we introduced this year the OpenFlex D4000, the OpenFlex C2000, or 1000, which are the C1000 and 2000 are compute nodes. The D4000 is actually hard drive based. So Nvme over Fabric attached hard drive modules or disk arrays, sleds we call these actually. So we had a 1RU pizza box style hard drive array, which we were shipping last year in conjunction with the F3000. We've decided that that wasn't dense enough, so now we're working on this D4000, so look out for it soon. But basically, this was a picture of our rack, more or less, at Flash Memory Summit. And as I said, the F3100, which is the flash module that plugs into the E3000, which is the 3RU chassis with the capabilities that I mentioned before. The Xilinx computational storage device, which is, so it's a storage coprocessor. So what we envision too is that rather than going remote to your storage all the time, with some coprocessors or compute very close to the storage, we're going to offload certain features. I don't know, we can do deduplication, we can maybe fetch data from a database table without having to do it at the CPU. We can just provide the results to the request, potentially. There's different ideas around this. And it's about sort of moving some of the processing power to the edge as well, rather than having it always centralized. So Dyticom as well, they're helping us, and they've built a prototype that supports open composable infrastructure. Coming soon is the D4000, as I mentioned. These are our two prototype compute nodes, the C1000, which is 1RU, and the C2000, which is 2RU. Very soon to be released is a new 24-bay Ethernet JBOF, which is basically Nvme over Fabric attachable, just a bunch of flash actually. So there's 24 SSDs in it, and rather than, traditionally you'd get a storage JBOD or something and you'd connect it to a computer via SAS cables. With Nvme over Fabric, it's the same thing. You're basically just connecting it via Fabric cables to a network adapter. Okay, so we're big on this open composable, so that this is a very real brand. We want people to contribute and to be on board with the idea of the interoperability. Here's a vision of the API. We have a lab in the University of New Hampshire where they run an interoperability lab, so people that are interested in open composable infrastructure are welcome to go there and test their products. So we foresee this future where all Fabric attached devices are peers and you compose them as you wish. And I've sort of gone through that rather quickly in the interest of time. How am I going with time, Sydney? Bang on. Whoops. I will close basically thanks to our open composable ecosystem partners, particularly Mellanox. And this is a resource slide, so when the slides are shared, have a look. There's some interesting links here, including the SNIA presentation, which goes a bit more into IWARP and Rocky. And on that note, I'll conclude. Is there any questions? You can always come and see me later and fry my brain. Thank you.